Okay, boys plus Vera, this is my attempt to, oh dear, this is not the correct date. It is definitely not 2019 anymore. This is my attempt to rectify what ended up being a confusing mishmash in class. And so I will do that right now, okay? This is what I was hoping to leave you with in class. Two very simple ideas that I managed to not make simple in its transmission. Oh, makes me feel badly. Anyway, okay. I'm going to do number one from page 190 here, all right? If you have your textbook or your iPad, George, or anything like that, just pull that out, all right? But here's the premise. You're given the following. You're told that V is the set of all ordered pairs of real numbers, all possible ordered pairs of real numbers, okay? So V is all the ordered pairs of real numbers. And then they're told here too, they're just defining two elements in that set V, and they're calling them vectors, okay? They're saying, let vector U be this ordered pair, and vector V be this ordered pair, okay? And they are defining addition and scalar multiplication this way. They're defining addition traditionally, right? Addition is defined as it traditionally is. And here they're defining scalar multiplication to be this. So if you multiply K times an ordered pair, the result is going to be 0 as the X coordinate, and then that scalar multiple times the Y coordinate of that ordered pair, okay? So in part A, the question is just saying, given this defined set and these defined operations, okay, given a defined set and a defined operations, these two, find the additive transformation and the scalar multiple transformation on two given elements in the set. And they also gave you a scalar 3. Okay, very straightforward. I don't know how I managed to make just straightforward idea a disaster. Actually, no, I do know how I made that. As Andrew and Jack pointed out to me, I was very careless and incorrect in my sentence use on page 2 of your notes. Anyway, here we go, okay? So if this is U and this is V, by the definition of addition, U plus V will merely equal, right here, the sum of the X components plus the sum of the Y coordinates, right here, okay? Similarly, 3 times vector U, and again, vector U is given to us here, will be 0, 3 times 2, as per the definition up here, okay? And this is the result, okay? Then the question is, is this set being this set right here, is this set closed under the operation of addition and scalar multiplication as it is written here? In other words, if any ordered pair of real numbers, right, if any of them is added to one another in this fashion, or if any one of those ordered pairs of real numbers are scalar multiplied in this fashion right here, when you look at the results of those two operations as their definition, if you look at those two results on any of the elements in this set, will the result always be an ordered pair of real numbers? The answer to that question is yes. In this case, the set V is closed under the stated operations, or let's use this, the stated transformations of addition and scalar multiplication. Because any output from those two stated transformations will yield an ordered pair where each of those coordinates is a real number, okay? That is all I wanted to say today in class. Just the idea of testing closure of a set under transformations. All I wanted to leave you with that day was the idea of testing closure of a set of objects under the stated operations of addition and scalar multiplication. Just these two. So I will say I sincerely apologize for making what was such a simple endeavor so complicated. Okay? Now, let's go to a second example. Let's take a look at this. Here is S. S is the set of all ordered triples of real numbers. Okay, S is the set of all ordered triples of real numbers. Addition is defined as standard. And if I were going to write this out, when you're told addition is defined as standard, you could do this. You can say, if U equals U1, comma, U2, comma, U3, and V equals V1, comma, V2, comma, V3, the stated definition of addition for this problem is going to be, is going to be this. U plus V is stated as U1 plus V1, comma, U2 plus V2, comma, U3 plus V3, okay? All right, so that is the stated transformation of addition, and here is how scalar multiplication is defined. Scalar multiplication is defined as such, okay? Now, the question here is this. Here's my question to you. Is this set closed under the operations of addition and scalar multiplication as they are defined here? That's my question for you. Let's work through here. Here I did this, okay? I just said, let ABC be an ordered triple in the set S, and let DEF be another ordered triple in the set S, okay? Does ABC plus DEF yield an ordered triple where the coordinates are real numbers? Is ABC plus DEF an element of S? The answer, of course, is yes. Okay. The other question is, does K times ABC, which results in K squared A, K squared B, K squared C. Notice here, when you're given this definition here and you're not given any kind of limitation on the scalar value of K, unwritten but understood is that K could be any real value, real value. K cannot be I, okay? K could be any real value, all right? Well, is the output here an ordered triple with real coordinates? The answer is yes, okay? So again, given this set and these stated transformations as defined, this set is also closed under addition and scalar multiplication. Is everyone all right? Okay, very good. I'm going to go down and give you a final example now. Let me pause for one moment. Okay, here we go. Here's a question I just made up just now, okay? Let S be the set of all real ordered pairs, and addition is defined as such, and scalar multiplication is defined as such. Is this set closed under these two transformations? Go ahead and try it on your own, and then replay me for the answer. Okay, here is the answer. In the case of addition, if U and V are ordered pairs, right? U1, V1 is going to be real, as will U1, V2. So S is closed under addition. Okay, there is no way that you can multiply two real numbers and not get a real number. So S is closed under addition. This case, though, if you look at how scalar multiplication is defined, this is not closed. This set S is not closed under scalar multiplication because it is possible. So for example, let's let one of the elements in S be this. Let U equal, okay, my goodness. Oh no. Oh, here, good. 2, comma, -7. Okay. If U is 2, -7, under this transformation of KU, or, KU. Oops. Okay. Let K be an even integer. Then it happens to be the following, that K times U will result in K squared times 2, comma, the kth root of -7. And you will notice that this entity right here is not a real number. So in this case, this set S is not closed under scalar multiplication. Okay? All right, Now, here is where I'm going to now move on. So as far as in class today, that was all I intended to talk about, was just testing whether a set was closed under different definitions of addition and scalar multiplication. So I have officially redressed my wrongs. Now I'm going to move on. You'll notice here that when we looked at these sets, for some reason that you may be wondering, maybe you're not wondering, I don't know, and Arjun, do not play me on double speed. Thank you. You're probably wondering, why is it that all these elements of the set, why is it that we use these vectors? Like, why are we using kind of vectors to describe the elements of the set, okay? And the answer is because we are moving into looking at special sets that are called vector spaces. So the reason why I'm using vectors now is because it's just getting us in the habit of doing something notationally that we don't have to adjust to later on. The other thing is what a vector is. A vector could be anything that we want it to be. I mean, I'm here naming a vector to be this ordered pair, but even in the example of the set of people in our linear algebra class, so Jack, Arjun, Vera, etc., right? I could also just say that one of the elements in my set here, I can call that vector u. Like I can call the u vector, I mean, I could call it Jack. So what a vector is here, I mean, it could be anything, okay? Now, for your homework, I'm going to do quite a bit of modification of the directions because your homework is in the vector space section. We haven't talked about vector spaces yet, all right? What I want you to do, though, is the following. Okay, so for homework, I want you to do these questions here. These three, 2A, B, and C, don't require any modified instruction. For these 4, 8, and 9, I want you to ignore the directions in the text. All I want you to do is take the set that is defined for you in each question and test the closure of addition and scalar multiplication as they are traditionally defined. So for all of these, I want you to look at testing those sets for closure under the traditional definitions or standard definitions of addition and scalar multiplication. Okay? Okay. Let me finish writing this down. Good. Okay, I changed it. I don't want you to do number 9. Instead, I want you to do number 12. Okay, so 4 and 8, traditional definitions of addition and scalar multiplication. Number 12, what I want you to do is test closure of the set of polynomials under the transformations as defined. So in number 12, they tell you what the set is, and then they define addition and scalar multiplication for you in the question. Okay, so in other words, for these 3 questions here, I want you to disregard the kind of paragraph instructions at the very start and follow the instructions I just said. Okay, I will also say this, boys plus Vera, I do expect, even though I did go awry and I did not do a satisfactory job at the end of class today, I sincerely apologize. You know, when moments of aberration, or when there is something that doesn't go as expected, I absolutely do make sure to make every effort to redress and correct. I also expect the same of you tonight when you do this homework. Okay, so please now that we've looked at this and we've hopefully cleared everything up, please give this some good work, and I will see you on Monday. Have a wonderful weekend, boys and Vera. Goodbye.